All right, everyone, welcome. In this video, we're going to be talking about calling conventions. Before we get into that, we'll talk a little bit about stack frames and what a stack frame is. And hopefully, you've heard the term before or you've read about it in some of the assigned readings. Even if you haven't, you've been working with stack frames since you started programming or working with assembly. So, what a stack frame is a way in which we can conceptualize how the stack is being used for a specific function call. And so we know that when a function is called, oftentimes the stack is involved in the execution of that function. We push the return address on when we call the function. We store the old value of EBP. Arguments are pushed on. We have local variables. We might have a stack cookie or a stack guard. In addition, if a function modifies a register, it might save the status or save the data in that register and restore it later on before the function returns. And so the stack is used for a lot of things when it comes to the invocation of a function. When a function is not executing, it doesn't really require any space, very little to no memory at all. And so the stack frame allows us to kind of conceptualize, again, how that stack is being used for that particular function. The stack frame and the stack itself also allows for recursion, and that when we want to call a function recursively, we just create a new stack frame, right? We call the address, we push on the return address, we have arguments, we have local variables. This just goes on top of the stack, and the stack frame, the information, the locals, the arguments, the old value of EBP, the return address, that's all still there from the previous function. And so every time we call a function recursively, every time we call a function in general, we create a new frame. When we're done with that, we clear the frame, and we can essentially restore the old one. We know where that function came from and where it needs to return. And the stack is that core data structure in memory that allows us to do that. So we know that when a function is called, all of these things happen. Parameters are placed on top of the stack per the calling convention, and that's really what we want to get into and stress today, is this calling convention will dictate how the stack is used for the arguments to that function. This is likely going to change the stack pointer, so keep in mind that ESP is always going to be pointing to the top of our stack. Once the function is called, transfer is controlled to that address where that function resides. Okay, inside that function, we'll have the prologue. We might have stack guard or the stack cookie being calculated. The code itself, because it's going to use registers, it might save those. So we see push EBP as part of the prologue, and then as part of the epilogue, we see pop EBP. Well, you might also see push EAX, push ECX, push EDX, push ESI, whatever. If a function is going to use those registers, then they may push those on to save them, use them, and then as part of the epilogue, essentially pop those values, restore those values. So that way, if something else was using it before that function call, that data wasn't destroyed. Space is going to be allocated for locals if locals are present. If there are no local variables inside that function, then the space simply won't be allocated. The operations, typically when a function returns, is going to return a value in EAX. That's our generally the register that we're looking at. And of course, this is important because when we're looking at disassembly, we're looking for functions that return a value. We're looking for a function call, so a call instruction with an address with the name of that function, and then we're looking for the use of that EAX register after that function call to see, are we using that, are we storing that in a variable, are we using that for comparison, is something being used, because likely that means that that function returns something. Okay, the function epilogue, registers are restored and then return. We'll ret, and that's the command, that's the instruction that returns execution, pops the address off of the stack, the return address moves it into EIP, that takes us back to where that function was called, the next instruction from where that function was called. Okay, so this and I think this is a diagram out of Practical Malware, I think does a really good job of helping us to visualize or conceptualize the stack frame. So here you can see that we have memory. This is the area of memory in our program for the stack. Keep in mind that they have these upside down compared to what I do, that our higher addresses are at the bottom, lower addresses are at the top. And so we're going from lower to higher as far as this diagram is concerned. And typically when I draw those, right, we'll just do my little stack thing here, I typically draw from higher to lower. It's exactly the same, we're just looking at it differently. based off of the addresses. So here you can see that on the stack we have the caller's caller stack frame, then the caller stack frame, then the current stack frame. And this shows us that stack frame. So we have arguments right here. We have the return address, we have old EBP, maybe we'd have a stack guard, then we have our local variables, right? This is what constitutes a stack frame. And if we look at that in the way that I typically draw them, we'd have arguments, we'd have return, we'll just call that ret, we'd have old EBP, and and then we'd have locals. Same thing. Everything that that function needs in order to execute. Okay, what comes above this one? Well, that's another stack frame. So we'd have locals, we'd have EBP, we'd have return, and then we'd have arguments. Right? We'd have another stack frame, and that's what comes above that space on the stack that we don't always focus on. Generally when we're talking about a function, we focus on its stack frame instead of the one that's previous. And so hopefully this is just kind of tying all of that together, tying all these concepts together. And so that's what you can think about, each one of these stack frames. That's the information that it contains. Okay, so in understanding the creation of a stack frame and how that stack frame is going to be used, how the stack is going to be used for a function, we need to understand how arguments are placed on the stack, or how arguments are passed to that function, because they're not always going to be passed on the stack. And these calling conventions are going to be our way of understanding how there are other ways of passing those arguments than just the stack. So the calling convention then dictates where the caller should place parameters that a function requires, right? The caller. We have three primary places, we're going to talk about. The stack, in registers, or a combination of those two. So not only is it important to understand how we place the information, the values for the arguments on the stack and the registers or a combination thereof, it's also important to understand how they're cleaned up, because we have two ways in which we have to worry about cleaning up the stack. We have the caller or the callee, right, which are these two bullets here. And we'll look at two examples. We'll look at a handful of examples here to help solidify these concepts. So the first calling convention that we'll look at is the C calling convention. And you'll oftentimes hear it pronounced, or at least I pronounce it this way, CDECL. So the C calling convention, used by most C compilers. And this is generally that when you compile a program, when you're looking at the disassembly of a program, this is the convention that you're looking at. We'll look at some examples here, and it should look pretty familiar. What happens is the stack is used for arguments. The stack alone is used for arguments. So the caller is going to place the parameters to the function on the stack, and they're going to push from right to left order. So you'll see here in a code example in just a second. So the caller, that means the person that's going to invoke that function pushes things onto the stack, and also when the function is done, the caller removes the parameters from the stack. Okay, both of these bullets here, we're talking about arguments, parameters, the same thing, values that we're passing for that function. Okay, when it comes to this right to left order, what that means is that we push the last argument first and the first argument last. And so you'll see in this example, I have a demo function, and it takes 4 arguments. So if I pass it 1, 2, 3, 1 is the leftmost, it's the first, but I push the rightmost, which is 3 or 4, whatever said was last. Okay. The other thing is the caller cleans up, and you've seen this plenty of times now. Likely you talked about it in an assembly course. Is that after the call to that function, you'll see an adjustment to the stack to clean up, to essentially remove those parameters from the stack. Okay, so here's a more precise definition provided from, I believe, from Microsoft. Take a look at that. But here's our example. So you can see that I have, inside a main, I have one function right here, and I'm calling demo. I'm providing 4 values, 1, 2, 3, 4, in that order. Here's the function itself. There's nothing inside of it. We don't care about that. You can declare the calling convention, as I did here. And so you can see that when we call demo, I want to pass 1, 2, 3, 4 to it. when we look at this function then, we look at the assembly or the disassembly from that, we can see here's our call to sub 401000. Okay, so that's our call to demo. And you can see that we're pushing from right to left. So the last argument is pushed on first, push 4, then 3, then 2, then 1. The first argument is pushed on last. Okay, we call the function does whatever it does, and then when it returns, right here, you can see that the stack is cleaned up. It's the caller's job to clean that stack up. So what happens? Well, if we take a look, we can draw essentially a stack frame for this. We're going to push on the values, so 4, 3, 2, 1. Okay, remember that every time we push, we adjust the stack by 4 bytes on a 32-bit system. Okay, so a push is one way in which we move ESP. ESP is our pointer. It's always pointing to the top of the stack. Every time we push, we adjust. We adjust because we're creating space on the stack for whatever we pushed onto it. And now ESP is pointing to a different location, to the top of the stack. So we call the function. Okay, we know the normal prolog stuff happens. We push the return address on. We save old EBP. Maybe there's locals inside of there. When the function gets ready to return then, right, we execute the epilogue. We get back to a place where ESP is at EBP. We pop EBP back to EBP, so we restore the old value of EBP, and then what we do is then we return. And that pops, or the ret instruction, takes whatever's off the stack and it puts it into EIP. And so once we get back to this instruction, right, we've returned from our function, our stack pointer is right here. It's still pointing to the top of the stack, which is where those arguments are. So if we did not do this, let's say that we omitted this instruction right here, we'd XOR EAX with EAX, we'd pop EBP. Okay, we don't have to adjust the stack anymore because there was no locals, so we'd pop EBP. Well, what are we popping into EBP? We're popping 1. That would decrement our stack or move our stack pointer to here, would add to it actually, and then we return. What does return do? Well, it pops this off, moves it into EIP. Okay, obviously that's not the address that we want to return to. Our program's going to crash. So that's why it's important when we return that we adjust. So every time we push in 4 bytes. So we had 4 plus 4 is 8, plus 4 is C hex, plus 4 is 10 hex. So we need to adjust by that. So now we add to ESP 10 hex. So once that function's done, we adjust, we add higher and lower. So by adding, we're moving our stack pointer back up to here. Okay, what's up here? Well, the previous stack frame. So we have old EBP, and then we have our return address. So if we're pointing here, now when we pop EBP, we're restoring EBP. ESP then adjusts, and now when we return, we move that return address into EIP, and our program executes as it should. Okay, so that's the importance of this. You can add, you could pop as well, but it's probably more efficient to just add. And this is commonly what you'll see, right? This is commonly when the CDECL is used, and the compiler will generate the call and the add after that. Okay, this is basically what we just talked about. So I went through all this trouble of making this nice diagram, and then I promptly ignored it and scratched a bunch of doodles up on the previous slide. But this is the stack frame. So if we look at the difference here between the previous example and this is that I went just a little bit further and to say, okay, inside of sub 401000, which was, remember, that's demo, this is what our stack frame would look like. This right here. This to this. Here's our arguments right here. Here's our return address. Here's old EBP. And then here's anything else inside that function. Stack cookie, stack guard, saved registers, and local variables. Okay, so that's our stack frame for that. Okay, here's an example with printf. Pretty much the same thing we've been talking about. We have just different arguments. And so when we think about printf, right, normally the first argument is our format specifier. And then from there, it's whatever values we want to print. And sorry, that's really looks chicken scratchy, but it's harder than you'd think to write on this tablet. And that's what we're seeing here. Okay, so our printf call in this example would be %d, 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 %d. You can see that. I save that as part of the comment here with IDA. So we have the first argument is our format specifier, which is this offset ADDDD, 4 format specifiers. So we have the actual format specifier string itself, and then 4 values to print. So we have a total of 5 arguments. So the last thing, the last argument, pushed on first. So if I'm just trying to print 1, 2, 3, 4, 4 is pushed on, then 3, then 2, then 1, then the format specifier. Then we call printf, and now once that returns, the caller has to clean up the stack. 14 hex, right? With 4, we had 4 plus 4 is 8, plus 4 is C, plus 4 is 10 hex, plus 4 is 14 hex. And so this instruction right here is going to clean up the stack for us. Okay, next calling convention is the standard calling convention. And you can see STDCALL, or standard call. The difference with this one, it's somewhat subtle, but it's very important. We still use the stack to pass parameters. The parameters are still passed on in right to left order. So just like the previous calling convention, the difference right here is that the called function is responsible for clearing the function parameters when the function is finished. So what this means is that the function itself needs to know the number of arguments. And you think, well, seems obvious, right? Functions generally know that. But that's not the case. Think of printf. Printf has a variable number of arguments. So this calling convention doesn't work with everything. Okay, so let's look at this example here. Here you can see demo. Same exact function as the last time we talked about. The only thing is a different calling convention. So standard call. 4 arguments, their integer values, same invocation here, so demo 1, 2, 3, 4. So we look at the disassembly of that. We can see, just like we had in the previous example, we have the pushes, so push 4, then 3, then 2, then 1. So we're pushing from right to left. Now we have the call, sub 401000, so that's demo, and you can see here, here's the function itself. It doesn't do anything because I don't have anything inside of it. When that returns though, you'll notice that there is the caller is not adjusting the stack. We're missing that add to ESP right here after the call instruction. It instead will return immediately to XOR EAX, pop EBP, and return. This is where the difference comes in. You can see that inside of this function, it's a little bit different. The return has an operand. So ret n 10 hex. So what's going to happen is that when this returns, the callee will move the return address into EIP, and then it will clean up the stack before it returns, or as part of the return, right? So if we look at this from, draw our stack here, right, we push on our arguments, 4, 3, 2, 1. We push on the return, okay, which will return us right here to the XOR. And then we execute the prolog. So there's old EBP. And then we move ESP into EBP. In this case, everything is just pointing right here. So EBP and ESP haven't really done anything. Now we're ready to execute the epilogue, because again, this function didn't do anything. So now we pop into EBP. So this restores the old value of EBP. Right, so we don't have to care about EBP anymore. ESP is now pointing here. Okay, the next thing that'll happen is it'll return, so it'll pop this into EIP, so EIP knows where to go, and then it'll clear 10 hex off of the stack. So now ESP, after we did the return, it was pointing here to the very first argument, right? And that's the problem. That needs to be cleaned up. So 10 hex. So we'll move 4, 8, C, 10 hex, ESP will be pointing right here, which will be back to the previous stack frame, right? And so that's how that ret n plus that number, that operand, is helping to clean up the stack. Because again, if that didn't get done, we get the stack out of alignment, then it can cause the program to crash. All right, the last calling convention is fast call. The last calling convention we'll talk about is fast call. And this is a variation of the standard call. And what it will do is it'll pass up. This is the hybrid. So when I said that it'll use the stack, the registers, or both, this is using both, or it can use both. So it'll pass up to 2 parameters in registers rather than the stack. And most compilers recognize this, although not all of them. The reason that this would happen is for performance, and that it's quicker to use registers than it is to use the stack, to use memory. So the registers that are used, see right here, ECX and EDX. And if the function has more than 2 arguments, then the remaining arguments are pushed right to left onto the stack. Okay, so this can be either registers only, if it's 2 or less arguments. If it's greater than 2, then it can become a combination. So the first 2 values will be used in those, pushed into those registers. Everything else will be pushed onto the stack. So what you need to be able to identify when using the fast calling convention is that sometimes the registers are used. Okay, so here again we can see same example. The only thing I changed was the calling convention. So now it's fast call. It's still the demo function. I'm still invoking it with values 1, 2, 3, 4. Okay, here we can see though that we have push 4, push 3, move into EDX2, move into ECX1, and then the call to the function. And what I didn't show you is what it would look like if we jump to that function. But if we did, when we reference those arguments, instead of referencing, EBP plus arg 0 or plus arg 4 or whatever the case may be, how IDA usually identifies the reference to an argument for us, what we would see is we'd see the actual register being used. And so what you want to look for is that before a function is called, is data moved into a register? Okay. If so, when you look at that function, are those registers being used to move data out of? And if so, then likely it was used as a way to pass the arguments to that function. Okay, so don't think that the only way arguments are passed to a function is from the stack. And that is the big takeaway from this. It's not that important to remember which one's which, fast call, standard call, CDECL. What's important, really important, the most fundamental thing is that you can determine when a function and how a function is having parameters passed to it. Because if you look at this and say, okay, this function only has 2 values, 2 arguments passed, because you ignore these 2 instructions, then you might miss or misunderstand the functionality, the purpose of that function. Okay, there are other calling conventions. We'll talk about one primary one when we talk about C++ a little bit later. Oftentimes, though, they become very language compiler and CPU specific. So if you start to deviate or research from platforms other than what we've been talking about, you might have to look into that and do a little bit of research. The last thing that we'll look at here, and this is kind of a follow-up from one of the previous labs, I think from the first lab, and I think I went through this in the actual video, but just again to show you different ways in which, and to really stress different ways in which the stack can be referenced. Here you can see, and you probably noticed that you have this ESP plus 4C hex plus var 4C. And what this was doing, it seems very confusing, but what this was doing is we had ESP plus 4C, and so that was a shortcut, and one of these, I think the 4C hex was actually a positive 4C. Well, yeah, I'm sorry, it is, because it's an immediate value. Var 4C, on the other hand, was a label for minus 4C. And so if you take minus 4C and you add to it positive 4C hex, you get 0. So ESP plus 0 is ESP. And so what this is doing really was a way in which the top of the stack was being referenced. These cancel out. ESP is just ESP. ESP is just the top of the stack. And so what these instructions were doing, they were pushing ECX. It was arbitrary. That was just to make room, 4 bytes of room on top of the stack. And then this was a way in which to reference the top of the stack. Now, why do this instead of just referencing ESP? I'm not 100% sure. Sometimes compilers do things you don't expect. But That's what you were seeing there with those instructions. So again, I'm pretty sure I talked about that when we went through the review of Lab 1, but just in case I didn't, I wanted to make sure I touched on that. And even if I did, never hurts to review. Okay, so those are calling conventions. If you have any questions on those, let me know. Again, one of the key takeaways from today was that arguments aren't always passed on to the stack. So that's all I've got, and I'll talk to you in the next video.